grade 10 students. I know that you are done with statistics, and today we are going to learn another lesson which is fundamental in the field of mathematics.
What is the importance of trigonometry in real life? That is a very big question that needs to be answered. Well, my dear students, trigonometry has many applications in the modern world. Without it, many modern industries and sciences would simply not exist. Trigonometry is commonly used in finding the height of mountains, towers, and distance of the shore from a point in the sea. It is also used in oceanography in calculating the heights of tides in the oceans, and it is used to find the distance between the celestial bodies and other objects. That's how useful trigonometry is. Are you got trig? Well, just sit back and relax because we are gonna learn the fundamental trigonometric identities. Speaking of identities, what is an identity? An identity is an equation which is true for all values of the variable for which both sides of the equation has a definite finite value. Let's have an examples. X plus 1 equals to 1 plus x. The quantity of x minus 2 times the quantity of x plus 2 equals to x squared minus 4. In both examples, any value of the variable x will satisfy both sides of the equation. That makes the statement true. Some people ask, where did it come from? How did they derive the identities? Have you ever wondered also, grade 10? If yes, well, get ready of yourself because we are going to derive the different identities. But let us recall first what is a unit circle. A unit circle has a radius of 1 with its center located at the origin of rectangular coordinate system. This is how unit circle looks like. The vertical line is the y-axis and the horizontal line is the x-axis. The red line represents 1, which is the radius, and the point of origin is 0. The vertical line represents the y-axis. The horizontal line represents the x-axis. Y is perpendicularly to x value, which results to 90 degrees. And the angle is what we call the angle theta. From the information of the unit circle, we can already derive the three main categories of trigonometric identities in which you should become familiar. The first one is the reciprocal identities. The next one is the ratio identities. And the last one is the Pythagorean identities. Let us go first with the reciprocal identities. The sine theta, which is defined to be opposite side over the hypotenuse. The opposite side is the y over 1, which is the hypotenuse. Then, sine theta is equal to y. How about the cosecant? The cosecant theta is defined to be the hypotenuse over the opposite side. The hypotenuse is equal to 1 and the opposite side is equal to y. That's why it's 1 over y. Then, because y is equal to sine theta, then we can say that cosecant theta is equal to 1 over sine theta. Therefore, cosecant theta is equal to 1 over sine theta. Now we already derived the identity number 1 of the reciprocal identity, which is cosecant theta is equal to 1 over sine theta. And it can also be written as sine theta equals to 1 over cosecant theta, which is also equal to sine theta times cosecant theta equals to 1. They are just equal. Now let's move on to the cosine. Cosine theta is defined to be its adjacent side over the hypotenuse. The value of the adjacent side is x over 1, which is the hypotenuse. Then cosine is equal to x. We can conclude now that cosine theta is equal to x. How about the secant theta? Secant theta is defined to be as the ratio of hypotenuse and adjacent side. The hypotenuse is equal to 1 over the adjacent side, which is x. Therefore, secant theta is equal to 1 over cosine theta. Then we can conclude that secant theta is equal to 1 over the cosine theta. We now derive the identity number 2. Secant theta is equal to 1 over cosine theta can also be written as cosine theta is equal to 1 over secant theta. And cosine theta times secant theta equals to 1. Now, let's move on to the tangent. Tangent is defined to be as an opposite side over the adjacent side. The opposite side is the y, and the adjacent side is the x. Because y is equal to sine theta and x is equal to cosine theta, that's why we derive that tangent theta is equal to the sine theta over the cosine theta. How about the cotangent? If we get the cotangent theta, because cotangent theta is defined to be its adjacent side over the opposite side, then the adjacent side is equal to x and the opposite side is equal to y. Then the x is equal to cosine theta and the y is equal to sine theta. Then we can derive that cotangent theta is equal to cosine theta over sine theta. We already derived the identity number 3, which is tangent theta is equal to 1 over cotangent theta. If we are going to derive why is it that tangent theta is equal to 1 over cotangent theta, this is how it works. Tangent theta is equal to 1 over cosine theta over sine theta. Then the tangent theta is equal to 1 times the reciprocal of the denominator, which is sine theta over cosine theta. Tangent theta is equal to sine theta over cosine. That's why the tangent theta is just the reciprocal of the cotangent theta. Cotangent theta is equal to 1 over tangent theta. Then it is also written as tangent theta times cotangent theta is equal to 1. Now let's move on to the ratio identities. Identity number 4, which we are already derived, the tangent theta is equal to the sine theta over cosine theta. The alternative form is cosine theta times tangent theta is equal to the sine theta. Cosine theta is equal to sine theta over the tangent theta. Then, the fifth identity is cotangent theta is equal to cosine theta over sine theta, which can also be written as sine theta times cotangent theta is equal to cosine theta. Another form, sine theta is equal to cosine theta over the cotangent theta. Now let's move on to the Pythagorean identities. The Pythagorean theorem. The square of the hypotenuse is equal to the sum of the squares of the other two sides, which is the hypotenuse is 1, so 1 squared is equal to x squared plus y squared. Because we know already that the x is equal to sine and the y is equal to cosine, that's why we can derive that sine squared theta plus cosine squared theta is just equal to 1, and that is a Pythagorean theorem. Then the identity number 6 is sine squared theta plus cosine squared theta is equal to 1, which can also be written as cosine squared theta is equal to 1 minus sine squared theta. Sine squared theta is equal to 1 minus cosine squared theta. Take note, in sine squared theta plus cosine squared theta equals to 1, be aware that sine squared theta means the quantity of sine theta to the power of 2 is just equal to sine theta times sine theta. Please do not put the exponent to the angle because we are not squaring the angle but the sides or the length of the triangle. If we divide both sides of the sine squared theta plus cosine squared theta equals to 1 by cosine squared theta, we have the sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals to 1 over cosine squared theta, which results to the tangent squared theta plus 1 is equal to secant squared theta. Then we already derived the identity number 7. That is tangent squared theta plus 1 equals to the secant squared theta. It can also be written as tangent squared theta is equal to secant squared theta minus 1. Then also written as secant squared theta minus tangent squared theta is equal to 1. We divide both sides of the sine squared theta plus cosine squared theta is equal to 1 by sine squared theta, we have sine squared theta over sine squared theta plus cosine squared theta over sine squared theta is just equal to 1 over sine squared theta. Then we already derived that 1 plus cotangent squared theta is just equal to cosecant squared theta. The last identity is the identity number 8. Then we already derived the identity number 8. That 1 plus cotangent squared theta is just equal to cosecant squared theta. And cotangent squared theta is just equal to cosecant squared theta minus 1. It can also be written as cosecant squared theta minus cotangent squared theta is just equal to 1. I have here the summary table which contains all the identities, the reciprocal identities, the ratio identities, and the Pythagorean identities. I think that you are already ready for our illustrative examples. Illustrative examples. Simplify the following using the identities in terms of sine or cosine. Number 1, cosine x times sine squared x minus cosine x. Number 2, cosine x over 1 plus sine x over cosine x.
Let's have example number 1. Cosine x times sine squared x minus cosine x. By this expression, we can get the cosine x. Cosine x times sine squared x minus 1. That is through monomial factor. Then, by this expression, we can factor out negative 1. Then it will become negative cosine x times the quantity of 1 minus sine x. Then, this one, by 1 minus sine squared x, because of the Pythagorean identity number 6, we can write this 1 minus sine squared x as cosine squared x. That's why negative cosine x times the quantity of cosine squared x. By this expression, we can simplify this one as negative cosine cube x. This is the final answer. Let's have example number 2. Cosine x over 1 plus sine x plus sine x over cosine x. By this expression, in order for us to add this expression, we have to get the LCD. That is 1 plus sine x times cosine x. Then we can divide this LCD to this one and multiply to the numerator. So this denominator divided by this first expression 1 plus sine x times cosine x, the 1 plus sine x will be cancelled out. So what is left is cosine x times cosine x plus this denominator. By dividing this denominator also, multiplying this numerator, we can get the expression of sine x times 1 plus sine x, because the cosine x will be cancelled out. And what is left is 1 plus sine x times sine x. Now we can distribute this expression. Cosine x times cosine x, that is cosine squared x, plus this one by distributive property of equality, sine x times 1 will be sine x, then sine x times sine x will be sine squared x, over, copy the denominator, which is 1 plus sine x times cosine x. Now, by the definition of Pythagorean theorem, by the definition of Pythagorean identity, it states that cosine squared x plus sine squared x is equal to 1. So we can write this cosine squared x plus cosine squared x plus sine squared x is equal to 1. Then bring down the sine x over, copy the denominator, which is 1 plus sine x times cosine x. Then, by this expression, we can simplify this one, because these two expressions are equal, then we can just cancel out. So this is equal to 1. So what is left is just cosine x. So the final answer is 1 over cosine x.
Verify the following identities. In order for you to prove the identities easily, here are the general rules in proving identities. The first one, manipulate the more complicated side and try to reduce it to the exact form of other side. It is more convenient to express functions in terms of sines and cosines. Number 3, be familiar with basic algebraic manipulations like factoring, squaring, combining terms, and reducing complex expressions. And the last one, be thoroughly familiar with the 8 fundamental trigonometric identities.
Number 1, cosecant squared theta minus 1 over cosecant squared theta is equal to cosine squared theta. We need to identify first which side is complex or complicated in order for us to verify. This one is the most complicated. That's why we need to verify this one to get cosine squared theta. Now we write this as cosecant squared theta minus 1 over cosecant squared theta is just equal to, from Pythagorean identity number 8, that states that cosecant squared theta minus 1 is just equal to cotangent squared theta, over, we can write this expression, cosecant squared theta. Then this one, cotangent squared theta, by reciprocal identity, we can write cosecant squared theta is just equal to sine squared theta. So cotangent squared theta times sine squared theta. That is by reciprocal identity number 1. Now, we can simplify cotangent squared theta by the ratio identity number 5. Cotangent squared theta is just equal to cosine squared theta over sine squared theta times the sine squared theta. Then we can simplify this one and we can cancel out sine squared theta. Then what is left is just cosine squared theta. Okay, let's have example number 2. That is cosecant x plus cotangent x is equal to sine x over 1 minus cosine x. Which expression is more complicated? That is sine x over 1 minus cosine x. So let's prove this one, that is just equal to cosecant x plus cotangent x. So sine x over 1 minus cosine x is just equal to sine x over 1 minus cosine x. In order to prove this one, we get the conjugate of the denominator and multiply the expression. That is 1 plus cosine x over 1 plus cosine x. Now, we distribute sine x to this one. It will result to sine x plus sine x times 1, that is sine x. Sine x times cosine x, that is sine x times cosine x. That is distributive property of equality over 1 minus cosine squared x. 1 times 1, that is 1 squared. This is just equal to 1. Then minus cosine x times cosine x, that is negative cosine squared x. Then we can simplify this one as sine x plus sine x times cosine x over sine squared x. By the definition of Pythagorean identity number 6, that sine squared x is just equal to 1 minus cosine squared x. Then we can separate the fraction, that is sine x over sine squared x plus sine x times cosine x is just over sine squared x. This will become 1 over sine x plus we can cancel out the sine, then cosine x over sine x. This one is just the reciprocal identity. The reciprocal identity, 1 over sine x is just equal to cosecant x plus cosine x over sine x is just equal to cotangent x. So this is the final answer.
Evaluate number 3.
Let's proceed to number 3. Let's evaluate the expression. Okay, the solution is, since cosine theta is greater than 0 and the sine theta is less than 0, it is in the fourth quadrant. If we try to draw a Cartesian plane, this is the x and this is the y. Since cosine is just equal to x, then it is said that it's greater than 0, so the cosine, the value is here. And since sine is just equal to y, and it's stated that sine theta is less than 0, so the values are here. That's why the given number is in the fourth quadrant. The given is sine theta is equal to negative 3 over 5. Now the given is sine theta is equal to negative 3 over 5. Using the cosine squared theta plus sine squared theta is just equal to 1, we can find the cosine theta. Cosine squared theta is just equal to 1 minus sine squared theta. So the cosine theta 1 minus sine squared theta. 1 minus the value of the sine, that is negative 3 over 5. The value of this sine is negative 3 over 5 squared. 1 minus, you square this one, this will become 9 over 25. 1 minus 9 over 25 25 divided by the denominator 1 is 1 times 1 is equal to 25 minus 25 divided by 5 is 1 times 9. This will become 9. 25 minus 9 is 16 over 25. Then plus minus square root of 16 over 25, this will become 4 plus minus 4 over 5. Now the value of cosine theta is positive 4 over 5. Why? Because the cosine states that cosine theta is greater than 0. That's why it is located in the positive Since cosine theta is greater than 0, that's why it is located in the positive axis. So the answer for cosine, the value for cosine theta is just 4 over 5. Now the value of the cosine theta is positive 4 over 5 because cosine in quadrant 4 is positive. Since we have already the value of the cosine theta and the sine theta, we can now get the value of the tangent theta. Tangent theta is just equal to the sine theta over cosine theta. That is in ratio identity. Then this will become the value of sine theta is negative 3 over 5 over cosine theta is 4 over 5. Simplify. This will become negative 3 over 5 times the reciprocal of the denominator, which is 5 over 4. This is just equal to negative 3 times 5, that is negative 15 over 20. The tangent theta is negative 3 over 4. Okay, now we already get the value of the tangent, which is negative 3 over 4. We already have the three values. Value for, we have already the three values. Value for the cosine theta, the sine theta, and the tangent theta. Since we have already the three values for sine theta, the cosine theta, and the tangent theta, we can now get the other three values by reciprocal identities. Cotangent theta is just equal to 1 over the tangent theta. 1 over, what is the value of the tangent theta? It's negative 3 over 4. Now, 1 times the reciprocal of the denominator, that is negative 4 over 3. Now, the value of the cotangent theta is just equal to negative 4 over 3. Okay, now let's get the cosecant theta. Cosecant theta is just equal to 1 over the sine theta. That is by reciprocal identity. Now we can get the value of the cosecant theta. Now we can get the value of the cosecant theta by substituting the value of the sine theta. The sine theta is negative 3 over 5. This will become 1 times the reciprocal of the denominator, which is 5 over 3. Now, 1 times negative 5 is just equal to negative 5 over 3. So, cosecant theta is just equal to negative 5 over 3. Now, let's proceed to the secant theta. In order to get the value of the secant theta, by reciprocal identity, 1 over cosine theta. It's 1 over the value of the cosine theta, it's 4 over 5. So 1 times the reciprocal of the identity, it's 5 over 4. This to become 5 over 4. So the second theta is equal to 5 over 4.
If you use the suggested general rules, you will never get into trouble in proving and simplifying identities. But we know that it is too optimistic to expect everyone will follow by the straight path. There will always someone who will come up with his own special way. Tricks and shortcuts are fine. That is how math works. Take note, everyone, you must never assume that an identity is true until you have proved it to be true.